Is that good? Yeah, sure.
We're starting our next presentation.
Okay, so today I'll be talking about kind of a more niche topic. It's called field-centric drive. And I'm Matthew Lee. I'm 17 years old. I go to Plano West Senior High. And starting this year will be my third year in FTC. And I'm team captain of Team 18227, Area 52, and I was a programmer before. So, yeah. So before we understand field-centric drive, I first want to talk about robot-centric drive, which is what we normally use when we're driving the robot. So basically, as you can see here, if you point the joystick forward, then the robot will naturally move forward. But it's not actually like absolutely forward. It's forward relative to itself. So if the robot was facing in the right direction, then it would travel in the right direction because that is forward for the robot. But if the driver was standing right here, then the robot wouldn't be traveling forward in the view of the driver. So what field-centric drive is that the robot travels forward in the direction of the driver instead of relative to itself. So as you can see here, if you push the joystick forward, then the robot will travel actually forward, not forward relative to itself. It will travel forward relative to what the driver is seeing. So that's kind of what field-centric drive is. It's basically saying that all four of the directions, the direction is absolute and it's not relative to the robot. So some of the pros and cons of field-centric drive are that, first of all, the pros, basically, field-centric drive is, it doesn't require you to know the heading of the robot, and robot-centric drive does. So when you're driving and you're looking at the field, you need to know which way the robot is oriented in order to drive correctly. But for field-centric drive, you don't need this. You can just drive without seeing which direction the robot is facing. And then field-centric drive is also a lot more beginner-friendly, and it's easier to control the robot right off the bat instead of robot-centric drive, which takes some more getting used to. Really, the only con about this is that most people that have already used robot-centric drive a lot, they think that it's easier and more comfortable because that's what they're used to. But in the end, everything just comes down to what you prefer and what the driver thinks is most comfortable. So now I'll be showing you basically how to implement it, kind of the math behind how field-centric drive works. So I go to the paint tool here. Okay, so let's say I have the robot here, and I'm going to draw a line here to denote that it is facing that direction. So then let's also say that I have the driver right here, and that I have the I'll just use the mouse. It's a little easier. Yeah, so so this is the robot, and then here's the driver, and then here's the gamepad. So let's just draw a dotted line here to denote that this is 0 degrees. And let's say that the driver points the joystick in this direction. And then that creates an angle here. Oh, whoops. That creates an angle here. And that's kind of scuffed, but we're just gonna call it theta J. And then, so then we also have the robot heading, which is pointing backwards like this. And so normally, if you point the joystick in this kind of upward right direction, the robot would move in this direction. But we actually want it to move in this direction because that's the way that the joystick is facing, actually. So then that means that we need to find the angle here, which I'll just call theta. And basically this is how much that the robot needs to turn, or this is the direction that the robot needs to go relative to itself in order to go in the direction that the joystick is actually facing. So if we take this angle right here, which is the heading of the robot, and we take this angle right here, which is the heading of the joystick, we can obtain this angle theta by just subtracting the two. Okay, that was bad. And so basically that's the equation that we have, right? And so theta r is the heading of the robot, which is already given to us. So we can just call the method get heading to obtain this angle. But the angle of the joystick is not given to us. And so this is an angle that we need to find. So to obtain this angle, we're going to use the x and y coordinates of the joystick, which are given to us. So if you took geometry, you would know that we can use trigonometry to find this angle if we're given the x and y values. So yeah, so we're going to use an inverse tangent function. And here, let me just write it out. Let's erase this here. So normally it'd be tangent theta equals opposite over adjacent, which is y over x. But we're actually going to flip this. It's going to turn into x over y instead, because 0 degrees for the robot is facing upwards instead of to the right. So the opposite side is actually going to be x, and the adjacent side is actually going to be y. And then we're also going to make this negative, because on the joystick, the coordinate system looks like this, and downwards is the positive right direction, which means upwards is the negative y direction. And so we need to reverse it and make it negative. Then in the end, let me just do j. We'll get theta j equals inverse tangent over negative x over y. Let's see if I can erase this arrow. So yeah, it's a little bit messy, but you can see that that's the joystick angle. So now we can find this angle theta, because we now have both the joystick angle and the heading of the robot. So we just subtract the two and we find it. But we're not done yet, because we can't just feed the robot an angle and have it go in that direction. We actually need to feed it x and y values. So if we take, let me just erase everything. So if we take this equation right here, this is actually the equation for field-centric drive. So then RB equals LF x minus y. So this is the equations for field-centric, or robot-centric drive actually. So this is the right front motor, left back motor, and then we give it the joystick x and y values. So negative x minus y, and then the right back motor equals the left front motor equals the joystick x minus the joystick y. So we can use this equation and replace this x and y with the x and y of the new theta, the new angle that we found. And that will be like the values that we can feed to the robot in order to implement field-centric drive. So how can we find this? Well, if we use sine and theta, or I mean sine and cosine, so we'll see that we can obtain both the x and the y value. So sine theta is going to equal negative x over c, and c is the hypotenuse. And then cosine theta is going to equal y over c. Oh wait, sorry, this is not negative. This one's negative, because y is the one that's flipped. And then normally this would be y over c, this would be x over c, But as I said earlier, 0 degrees is in the up direction and not the right direction. So it's going to be the other way around. And so when you look at this, you may think that, oh wait, let me just denote this first. This is new, the new x and the new y that we're going to be using. You may notice that we don't have this c, and we also don't have the x and y. So we have two unknowns in the equation. So we're not going to be able to solve it. But c is actually, it's the hypotenuse, right? So that means it's the magnitude. It's how much power, how much speed we want the robot to have. Do we want it to travel really fast or really slow? This doesn't concern direction at all. And direction is what we're trying to find. So that means the hypotenuse is going to be same for both the angle of the joystick and the new angle that we're going to be using. So we can simply just use the Pythagorean theorem for that. And we use the old x and y values from the joystick to calculate the hypotenuse. So we'll use, so c equals the square root of x squared plus y squared. And these x and y values are the x and y values of the joystick, not the new ones. So now that we can calculate c, we just need to take this x new and this y new and then isolate it and solve for those. So we multiply c on both sides for this one, for these two. And then for this one, you also multiply -1 on both sides. And so that's how you would obtain x and y new. And then after that, you can just plug in this x new and y new into this equation right here. And so if we go back to slides, you'll see that the final equation down here, it's kind of small so you can't really see it, but right front motor equals left back motor equals -x new minus y new equals -c sine theta plus c cosine theta. And then you would replace c with the square root of x squared plus y squared. And the subscript j means it's the x and y of the joystick. And then this new means that it's the x and y of the new angle that we found. So this is kind of like a summary of everything I did. We first need to find the angle theta that the robot needs to move relative to itself in order to move in the direction that the joystick is actually pointing. And then we can find that by using theta j minus theta r, which is the joystick angle minus the robot heading. And then step 2, we can find the angle of the joystick using an inverse tangent function. And then step 3, the heading of r is already given. So using those two, we can find what theta is. And then we take the robot-centric drive formulas, and then we replace this x and y with the new x and y. So we first need to find the new x and y. So we use cosine and sine to find that. And then we also need to find c, because we don't know what c is. But c is the same for both the joystick and the new angle that we found, because it's magnitude. And so then we get c, and then we solve for x and y here. And then in the end, we just replace c here with square root of x squared plus y squared. And then we replace this x and y with the x new and y new to get these two final equations. And so you just need to plug these pretty much into the code, and then you'll have field-centric drive. So yeah, that's all I have. Thank you.
So going back to the rationale of why you would do this, is field-centric, is driver-centric like video games, or is field-centric like video games?
Yeah, driver-centric is like video games, because like if you're controlling a character in a video game, the character would be like the robot, pretty much.
So that's driver-centric, you said?
That's like robot-centric, yeah.
So then that would be a reason why most people use it right now, just because they're used to gaming.
Oh wait, no. It would be driver-centric, because if you have a character facing to the right, and then you push forward on the joystick, the character would not move to the right, which is forward for the character. It would move forward in the direction that like the player sees it. Yeah, so it would be driver-centric. It would not be character-centric.
So that's the real reason why we should go through this long equation.
Yes, yes.
Implement that to make it better for gamers.
Yeah, sure. It's a lot easier to use,
Right.
is what people think. Yeah. Yes.
Have you ever made the robot FPV before?
Make it what?
FPV.
FPV?
So there's a camera on the robot that feeds back to the VR goggles that the drivers wear.
No,
That way they see exactly what.
That could be fun to implement. Maybe we could try it in the future.
Because I know they do it for RC planes.
Oh, okay.
But no, some teams have, they don't implement it in goggles, but they'll have it on the, I have seen it show up on the driver hub.
I know at FRS we want to put a camera on the robot and record all the matches. So do that.
Okay.
Have you ever used it in a competition?
No. I just basically made this formula over the summer.
You made that for me.
Yeah.
Awesome.
Here.
So since we're calculating theta J, so I'm assuming that by the end of your operation, your robot heading will be in your joystick heading as well, right?
What do you mean by that?
So you're calculating the motor powers. So after you're done with your coding and that turns your robot heading towards your joystick.
It will not. No, it won't turn the robot. It will the robot will travel in the direction, but it won't turn.
Okay, so that's only the trajectory.
Yes.
Okay.
Question.
Yes.
So, is it important for you to then, when you're placing the robot down for the first time?
Yes. It needs to be facing forward, exactly relative for the driver. Yeah. So that's kind of one of the problems for field-centric drive because that's implemented in teleop, right? So at the end of the autonomous period, whichever way your robot's facing, if you have field-centric drive for teleop, then whichever way your robot's facing at the end of autonomous is going to be 0 degrees. So.
And do you have an option to set the heading at any time?
Set the heading.
That would help, right? So let's say if it is not facing the right way,
Yeah.
then maybe get it back, pull it, make it 90 degree, and then reset the heading. Because that would
I think yeah, that's definitely implementable, and that's one of the solutions for the problem that you just mentioned. But yeah, you would just have a button where if you press it, it would reset the heading to 0. So yeah. Okay. Any other questions?
You can add rotational speed when you are controlling the robot. So when you use the gamepad, you will not only move in the direction that the driver wants it to go, but also eventually it's facing the direction. So because I think your current implementation is just making a move.
Yeah, it won't be facing the
still
direction.
Facing the
Yes,
any
yes.
other direction, right? So, but if you maybe add some kind of a rotational.
Yeah.
movement,
So one joystick you would use for movement, and another joystick you would use for turning, or you could use the side buttons for turning, rotating like this. Yeah.
Yeah, I understand, but in the algorithm, whether you can add some kind of a rotational speed when you are controlling the motor.
Oh, you mean at the same time?
At the same time?
Turn and move at the same time?
Right.
Yeah, so you would just I think you could just use both joysticks at the same time. So you would move one forward, and then you would use the other joystick to turn at the same time.
Okay, but what if you just use one joystick, because you are trying to make it move in the direction that you want it to move, right?
Mm-hmm.
So it would be ideal that you can also change the facing of the robot so that it will always point to the direction that you want it to move. I think it probably can do something like that. But anyway, just a comment, it's not a question.
Okay. All right. Thank you.